scholars and faculty and all participants. Welcome to today's FDP sessions on 5G. Today on 22nd April 2024, we have two sessions. First session is on 5G numbering, addressing and identities by Professor M. Dakshayini of BMS College of Engineering, followed by second session on India's role in international standards and WTSA 2024 by Sri Avinash Agarwal, DDG, TEC, DOT. Dr. M. Dakshayini is an accomplished academician with a distinguished career spanning over 2 decades. She obtained her bachelor's degree of engineering in computer science and engineering from SJCIT Bangalore University in 1993, master's degree in computer science and engineering with first class distinction from BMS College of Engineering, Bangalore University in 2000, as well as she holds a PhD in computer science and engineering from Dr. MGR University. Currently serving as professor and head of the Department of Information Science and Engineering at BMS College of Engineering, Bangalore, Dr. Dakshayini is a beacon of knowledge and expertise in her field. With a rich teaching experience of 26 years, Dr. Dakshayini has mentored several students, guiding them towards academic and research excellence under her supervision. 5 research candidates have been successfully awarded PhD degree, and she is currently mentoring research scholars in the realm of computer communications, algorithm, cloud computing, ad hoc network, IoT, and data sciences. Dr. Dakshayini's contribution extends beyond academia. She has delivered expert lectures at various seminars and workshops, enriching her academic community with her insights and expertise. She is also actively involved as a board of studies and board of examinations member for several prestigious institutions. Recognized for her scholarly contributions, Dr. Dakshayini has more than 50 peer-reviewed publications in international journals and has presented her research in 26 international conferences and 5 national conferences. Her innovative research has led to the publication of the patent titled Cooperative Proxy Server Architecture for Video on Demand and web servers using stochastic model-based client request management approaches to achieve reduced client waiting time. In addition, Dr. Dakshayini serves as a National Board of Accreditation evaluator, contributing to the enhancement of quality standards in higher education institutions across India. Dr. Dakshayini's dedication to advancing knowledge and fostering academic excellence underscores her commitment to the field of computer science and engineering, making her revered figure in both academia and research communities. With this short bio, I invite Dr. M. Dakshayini for the session on 5G numbering, addressing, and identities. Dr. Dakshayini, over to you. Please go ahead, ma'am.
Thank you, sir. Hello, good morning, participants. Today, we are discussing on the topics 5G identities. It is numbering, addressing, and identification. And most of the topics have been covered by Ashok Kumar sir. And we are actually revising it. We know why or how identities for anything, any entity is so important because I think it is visible. This is visible, the PPT.
Yes, visible.
Okay. Yeah. And as academicians, we know why we have to assign a roll number or university register number or seat number to the students when we are serving them with a quality education. Otherwise, even though they have their names, we assign them the roll number and seat number. We feel that is better than the names because it is unique. So whenever we have many entities handling or providing a service or managing with many entities, it has to have some unique identity. Only then we can identify it, authenticate it, and successfully we can provide the service. So in the same manner in 5G, we have different entities like user equipment and 5G network, that is including radio access network and network core and all the network elements. So every element or any you take any user equipment or the mobile, there are so many mobiles. Whenever we have a mobile and which wants to communicate with other mobile devices across the network, it has to access the network. So when any mobile device tries to access a network simply it cannot allow any device to access the network. It has to identify the device and it has to authenticate, only then it can allow any mobile devices to access the network. So in that case, that is why we have identities for all the elements or the various entities in 5G system or 5G network. So at UE level or the user equipment level, what are the 5G identities that we can have? These are some of the identities that I could get. There is IMEI is the International Mobile Equipment Identity, International Mobile Subscriber Identity, that is IMSI, and Integrated Circuit Card Identification Number, that is ICC ID, and the SUPI, Subscriber Permanent Identifier, and Subscriber Concealed Identifier, SUSI, and RSUKI, then Permanent Equipment Identifier, and Global Unique Temporary Identifier, GUTI. These are some of the identities that we will be discussing at user equipment level. So initially, whenever we purchase a mobile, we purchase a SIM card also. So in the when we have these many identities, we have a question: different parts of mobile should have these IDs, right? So whenever we purchase a mobile, in the mobile itself there will be some identity or identification number, and for SIM there are a few identification numbers. We'll see one by one. So each subscriber is allocated one 5G subscription permanent identifier, that is SUPI, for user within the 3GPP system. The 5G system supports identification of the user equipment independently. Each UE accessing the 5G system is assigned a permanent equipment identifier. And SUPI is not signaled on radio. It is encrypted in the form of SUSI. We'll see why it has to be encrypted. And the 5G system supports allocation of a temporary identifier. We'll see why this GUTI has to be allocated and from whom it will be allocated to user equipment. So as I said, any mobile device wants to communicate with any other mobile device, it has to access the network, and network has to identify that mobile device, and it has to authenticate as a legitimate device. Only then it allows it to access that network. So we have these various identifiers. That is, first one is IMEI, International Mobile Equipment Identity. It is a unique 15-digit serial number given to every mobile phone by a manufacturer. Since it is given by a manufacturer, this ID can be used to get information such as phone's country of origin or the manufacturer and its model number, or the process they've used to manufacture the mobile, and the quality of process that they have used. All this information can be obtained using this identity, that is IMEI. And then we have one more identity, that is ICC ID, which is Integrated Circuit CID. So here we can get a question: is IMSI same as ICC ID? Because both are components of SIM, but both are different. Where IMSI, that is IMSI, is given by a mobile network operator, that is used to recognize the subscriber actually, which cellular network your device may use or may access. Whereas this ICC ID is a number that recognizes the SIM card itself. And can we have, suppose a subscriber has more than one SIM card, does the device has more than one IMSI or same IMSI? ICC ID is an identifier that we use to identify or recognize the SIM card. Okay, and IMSI is the number that recognizes the subscriber. Suppose if subscriber has more than one SIM card, generally we have two slots in the mobile phone where we can have two SIM cards. Suppose we have two SIM cards, can we have the same IMSI or two different IMSIs? Anybody?
Same MC, madam.
Same IMSI. So can we have same IMSI even if we have two SIM cards from different network operators?
No, ma'am. We should have different MC.
Different MC for different. If we have two SIM cards from two different mobile operators, right? So that is why in telecommunication system, mobile network operator allocates this unique identifier to each SIM card, which is known as IMSI in case of 4G communication network, and it is called as SUPI, that is subscription permanent identifier in case of 5G. So that is whenever we purchase a mobile network operator assigns IMSI, that is for 4G network, and assigns SUPI for 5G. And even though we have this SUPI for which is uh, conformed to 3GPP network, it is based on IMSI, or it is IMSI based. Why it has to be IMSI based? Even though we have a SUPI which is meant for 5G, it has to be, or it will be generally IMSI based. Why it is IMSI based? That is, suppose generally we have here, I mean, we don't have the 5G coverage across India, right? We have a combination of 4G. We are running this communication with the combination of 4G as well as 5G. So sometimes whenever your 5G mobile wants to communicate with a 5G core, or 5G mobile wants to communicate with a 4G core, it cannot send SUPI for the identification or the registration. It has to send IMSI, because 4G core MMC cannot understand SUPI. It can only understand IMSI. So even though your mobile phone conforms to 5G, it has to send IMSI. That is why we have the SUPI is IMSI based. That is for internetworking with EPC. The SUPI allocated to the 3GPP UE shall always be based on an IMSI to enable the UE to present the IMSI to the EPC core, that is 4G EPC core. Only then MMC can understand it, and it proceeds with a further thing. So we'll see these two, the structure of IMSI as well as SUPI. So international mobile subscriber identity, that is for 4G, and subscription permanent identifier, that is for 5G, both are 15 to 16 digit number. It consists of these three components, that is MCC, mobile country code as the first part, which is followed by the mobile network code, MNC. That's MNC is a 2 digit if it is European standard, and it is 3 digit if it's a North American standard. So the length of MNC depends on value of MCC, of course, the mobile country code. And it is recommended that the length is uniform within the MCC area. And the allocation and assignment of this MCC is administered by ITU, that we have discussed, sir has already told. And the current assignment can be obtained from this link. And the assignment of MNC, that is mobile network code, is the responsibility of each national numbering plan administrator. And in India, it is a devotee. And MNCs are also ranges 90X. It is administered by ITU. And the remaining 10 bits, that is 9 to 10 digits, is mobile subscription identification number, that is MSIN, within the network's customer base. And this is also administered by the relevant MNC assignee to identify the individual subscriptions. And this actually identifies a mobile subscription within this a public land mobile network or the private network. So this is an example of how this MC looks. Suppose if it is the MC number 262045678910111. In this, the first three digits, 262 represents the identification of the country. Here it is Germany, and 04 is represents the mobile network code. Here it is Vodafone, and the remaining 10 digits represent the individual number of the user, that is mobile subscription identification number, which is other than the mobile number, that is not same as the mobile number. And this is the MCC for Thailand, and this is MCC for Bangladesh, that is 470, and this is MCC for United States, that is 313. It has one more MCC, and for India, as you know, it is 404 and 405. So what is this public land mobile network? It is a public network. So how do you identify, or how do you represent any network? How do you address any network? So any address, we say it should have a combination of a country code and the network operator code. So as usual, this is a combination of wireless, any combination of wireless communication services offered by a specific operator in a specific country. So that is the combination of MCC and MNC that is represented by public land mobile network, and it will be a part of local area identity, cell global identity, and also IMSI that you have already seen. The PLIN is a part of IMSI. And next we have the next identifier is a SUPI. That is, SUPI is globally unique 5G subscription permanent identifier allocated to each subscriber in the 5G system. So it is a globally unique subscription identifier given to any subscriber. So when it is globally unique identifier, we should be very careful with that ID. That, I mean, we should keep it in such a manner that it should not be accessible by any third party, right? As you know, if any UE wants to communicate with any other UE across the network, it has to access the network. That is a combination of RAN as well as core. So when it wants to access this network, it has to introduce that UE itself to the network first, and then it has to register itself in the network, and then only it can access the network and it can communicate with the other UE over that network. So for that to introduce itself or to get registered into this network, it has to give its identification. What's its identification number? It is SUPI. Suppose if it is giving this SUPI as it is, which is very important, it's a globally unique identifier of a subscriber. As it is, if it is giving to network, it will go in a plain text to the network. So if it goes to the network in a plain text, what happens? Anybody can easily, any attacker can easily access it once they get this unique global identifier of any subscriber. That mobile device or the subscriber can be easily hacked by a third party. It can be any active man in the middle adversary. So that is called as IMSI catching or SUPI catching. So in order to avoid this IMSI catching or to avoid this privacy breach, the SIM card is assigned with a temporary identifier, saying that or indicating that always don't use that SUPI, which is very important. Use this temporary ID for any kind of communication with the network or with any other device. So that is temporary mobile subscriber identity. TIMSI was identified as the given until 3G systems. Now, then for 4G and 5G systems, the temporary identifier GUTI was allocated. So the TIMSI was given by, used to be allocated by MMC, and the GUTI also will be provided by MMC. And in 5G, it will be TIMSI or the temporary ID GUTI will be given to 5G by AMF of the core network. After getting this temporary identifier, any device or any subscriber started using that temporary identifier for further communication over the radio access network. But there are certain situations where the authentication through the use of temporary identifiers may not be possible. In what those situations it is not possible is whenever the user registers with the network for the first time, because first time when it wants to register with the network, it has to give its actual ID, right? Or when, suppose if the visiting network is not in a position to resolve that mapping between IMC and SUPI also, it cannot use this temporary identifier. In both the cases, it has to re-register, it has to get that temporary ID again. So for that, it has to give its unique global identifier, that SUPI, to the network. And we have seen that is not a good idea to give that SUPI as it is in the plain text. So the SUPI will be generally encrypted by ECC, that is encryption algorithm, and then it will be sent. So SUPI is a ID, original ID, which will be with the UE, that will be encrypted to a SUPI, and then encrypt the SUPI, that will be a SUKI. Then that SUKI will be transferred over the network to UDM, and where it will be decrypted, and then it comes back. It comes back to AMF. AMF assigns the GUTI, and then it will be given to the user. So in detail, it looks like this. So UE will have that SUPI, that is unique, globally unique identifier, that will be encrypted using elliptic curve integrated encryption algorithm, and that encrypted SUPI will be SUKI. That SUKI will be given to AMF, but AMF doesn't have the key to decrypt it, so it will be sent to UDM through AUSF. And when it comes to UDM, UDM will have the key, because all subscription information of any subscriber will be stored in UDM. So it takes the decryption key and it decrypts it. After decrypting, it will get the SUPI, and that SUPI will be authenticated and given back to AMF. Now AMF, after receiving that SUPI from UDM, it generates a corresponding GUTI for that SUPI, and it maintains or it stores that SUPI and the corresponding GUTI in a table. Okay, because it will have so many SUPIs and GUTIs of so many mobiles. So it has to maintain that in a table. So that will be sent back to the UE, saying that yeah, the registration has been accepted, our registration process is completed. So once that is the process. So first it encrypts it, and then it goes to UDM, and after decrypting it will come to AMF. AMF generates the GUTI, and then it will be sent back to UE. Once UE receives this, that saves that GUTI for further communication, where it will not use its original global identifier SUPI. Then from then onwards, it starts using this GUTI for any kind of communication. Then it next time when it gives that GUTI to AMF, AMF can generate the SUPI back from GUTI by mapping in a table, and then it continues with other process. It sends it to the for the authentication with the UDM. Suppose if AMF is not in a position, or it is not able to map this GUTI to SUPI, in that case, AMF sends a request back to the UE saying that send the identity request. In that case, again, it has to send the encrypted SUPI in SUKI. So that then AMF, after receiving SUKI, it continues again, it sends it back to UDM, where it has a key, and it decrypts it and takes it back, and then it assigns the temporary ID. So this is how identity of a UE will be exchanged with the network, with a 5G core, and get the temporary ID. So after taking the temporary ID for further communication, it uses only that. And this is the same thing what we discussed. And SUPI has different formats depending on the protocol that it uses to convey the SUPI. SUPI type can take a different formats. So a SUPI, if it contains a network specifier identifier, it shall take the form network access identifier. So if it is using network access identifier, it is based on the user identification as defined in TS 23.003. Suppose if UE needs to send its SUPI to the network, for example, for registration procedure, it has to provide that SUPI in a concealed form, that is called as SUKI, that just now we saw. Suppose in order to enable the roaming scenarios, the SUPI shall contain the address of the home network. So address of the home network is nothing but combination of country code and the network code. So in case of IMSI based on SUPI. And for internetworking with the EPC, the SUPI allocated to 3GPP UE shall always be based on an IMSI to enable the UE to present the IMSI to EPC. So that is in non-standalone system, our 5G mobile device may have to communicate with a 4G core, or 4G mobile may have to communicate with a 5G core. So in that case, if 5G mobile is communicating with a 4G core, it has to present its ID as IMSI. Then we have this concealed subscription concealed identifier SUKI. So it is as the name itself says, the subscription concealed identifier. It will be an encrypted form, is a privacy preserving identifier containing the concealed SUPI. The UE actually generates a SUKI by encrypting SUPI with the public key of the home network. And where will be this public key? It is securely provisioned to the USIM during the USIM registration. And this is the scheme or format of the SUKI. SUKI has 6 components. First one is SUPI type. It has 0 to 7 digits. The type depends on, if it is 0, it is IMSI based, and if it is 1, the network specific identifier. If it is 2 and 3, if it is 2, it is a global line identifier. If it is 3, it is global cable identifier. 4 to 7 is reserved for future use. And then we have a next component, home network identifier. So if it is IMSI, then home network address is a combination of MCC, that is a country code, and the network code. And if it is network specific identifier, it is network access identifier based. And then we have a routing indicator, because if it is home network, I mean, actually the complete information about the subscriber will be stored in the home network UDM, right? So for any kind of registration or authentication, it may have to contact the home network. So for that, it has to specify the routing indicator, which is 1 to 4 decimal digits assigned by the home network operator and provisioned in USIM. So that allow together with the home network identifier to route the network signaling with SUKI to AUSF and UDM instances capable to reserve the subscriber. And then we have a protection scheme ID that actually mentions whether it is encrypted or not. So this also has 0 to 15 digits. If it is 0, it is null scheme. That is, it will be transmitted in a plain text form. It will not be encrypted. If it is 1, it is profile A. If it is 2, also profile B. That is which encryption scheme it is being used. Based on that, it is 1 or 2 will be mentioned. 3 to 11 reserved for future standardized protection. 12 to 15 reserved for proprietary protection schemes. So you can also, depending on your application, if you want to use your own encryption scheme or algorithm, you can use it. So for that, if you are using your own encryption scheme, you can mention the digit 12 to 15. Then home network public ID. Once it is, depending on the ID that you are selecting here, protection scheme ID, if it is 1 or 2, it will be, hello? It will be encrypted. So for that, it has to use a public ID that should range from 0 to 255. Then we have a scheme output, which is the form of a string of characters with a variable length of hexadecimal digits, depending on the used protection scheme. This is an encrypted string depending on what encryption algorithm or scheme that has been used. Say, for example, here it is IMSI 23415099999, where first 3 digits represents the MCC country code and the next 2 digits represent the network code, and MSISN is the rest 10 digits. The routing indicator, if it is 678 and the home network public is 27, then how do you represent this as SUKI form? So since SUKI form, it is a null protection. So null protection is null scheme, that is 0. So how do you represent that null scheme? So initially it should be represented as 0. And then we have a MCC 23415 network operator and 678 as a routing indicator. And this 00, since it is null scheme, that is not being encrypted. Since it is not being encrypted, we need not have to mention the key and the encrypted form. So the after that, we have this MSIS, and that should be written as it is. So this is the SUKI form of this example. And if suppose if we are using the scheme ID 1 or 2, suppose if it is 1, it is profile A. The SUKI
Excuse
for
me, ma'am.
profile, yes.
Ma'am, I have one basic question.
Ah.
This Suki, if it is there, why boot is required? Because anyhow, it's a concealed identifier, and it can be interacted everywhere. No one can hack this. Yeah, by using such an encryption standard. Why Booty and MC, I mean, extra overhead to the network?
SUKI is encrypted form, but you know, in IT, there is a possibility of decrypting it. But still, there's so much of research is going on. And whenever you find a very difficult encryption algorithm that has been hacked or uh, solved already, right? So it is better to
That's
have a
what, ma'am,
temporary
people say,
ID
no, ma'am, ma'am, people
to
say, no,
be.
ma'am, like we have such an encryption algorithm which cannot be broken for years together. So
Yeah.
such a thing can be involved in Suki also, right, ma'am?
Yeah, that could be done because recent days we have a public key encryption algorithm. So if we can use, probably we can avoid. Ashok Kumar sir may propose it in the next release. It is better to have a temporary ID where it will be changing. It keeps on changing with respect to the communication. So when you keep on changing the GUTI, the possibilities of hacking or getting the information about the original identifier is difficult.
Okay, madam. Thank you. Okay.
Yeah, can I add something more?
Yes, sir. Yes, sir. Sure, sir.
Okay. So, of course, what you said is right that adding temporary ID or GUTI on top of Suki use will really add more kind of a protection. Uh, in addition, if you look at the protection scheme ID on the screen, So there are multiple profile A, profile B, already given by 3GPP, some sort of what kind of key exchange. And there are certain numbers reserved. 3 to 11 is kind of a reserve. So as in when new schemes becomes like somebody comes out with new scheme and that is taken up at 3GPP, maybe they can include. So up to 11 they have. In addition, if you look at 12 to 15, it says that reserved for proprietary protection scheme specified by home operator. So this is where somebody can do some sort of innovation. Even academia can come out with a new protection scheme or new algorithm to protect, and that can also be used. So operators can use even the proprietary one or anything developed outside 3GPP also can be used. For example, we have started talking about quantum-based encryption techniques, right? So if that somebody is able to uh, come out, and that can also be fit into this schema. So, so 3GPP has given a lot of room to improve your security aspects. So
Yes,
these
sir.
are my points, and why the problem which we have, that why we are not able to use all these schemes in a public network, all because there are many kind of devices. So you have older devices, 2G, 3G, 4G, 5G devices, a variety of devices. So many of the devices are not capable of using very high level of encryption techniques. So some of the devices cannot even encrypt. So whatever. So that's why. So there is a problem that network has to allow some of the device which are not capable enough for any kind of encryption. So there maybe comes out the 0 1, the null scheme. That means there is no encryption at all. So even if you have a capability, but your network, considering large number of customers, do not have a device which can support, so they have to downgrade and work on a null scheme that is no encryption at all. So it all depends. Similarly, if you have lakhs of IoT devices, as we know that IoT devices are
Yeah, very
not very
restricted.
complex, very small form factor, has to consume less power, less cost. So I cannot think of putting a very high level of encryption. Maybe many of the devices will not have any encryption. So considering all aspects, all these things are implemented into the network. But yes, of course, if we feel that some of the uh, communications are really, we want to make it safe, it is for our, say, armed forces, and also we can always put a high level of encryption because standards allow that. Even you can put proprietary encryption which is created in India, owned by some Indian or owned by some public sector company. So those are possible for specific use cases. So thank you, that was my input. Any further question I'll be able to answer.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, please go ahead.
And the encryption algorithm that is now being used is elliptic curve integrated encryption scheme is one of the strongest encryption algorithms, sir.
Yeah, yes.
Yeah. And we have a SUPI type. This we have discussed already. And home network identifier. When SUPI type is IMSI, the home network identifier is composed of MCC and MNC. Of course, when the type is network access identifier, it is we have to specify the domain name. And the routing indicator is the 4 digits, and protection scheme is null scheme, and this also we have discussed. And key, whenever it is being encrypted, key has to be identified, and after encrypting, the encrypted string has to be given. And NAI format for SUKI, this also has these components. Whenever SUPI is defined as a network specific identifier, the SUKI shall take the form of network access identifier, that is NAI. So in that case, it has to mention a form username at relam. So when the SUPI is defined as IMSI, the SUKI in NAI form shall have the form username without realm. So assuming, suppose if the IMSI is 23415 and 0999 as the IMSI, where 234 is MCC and 15 is MNC, and the rest 0 to 9 digits are MSISN. The routing indicator 678 and the home network public is 27. NAI format for SUKI takes this form, that is type 0, MCC 234, dot MNC 15, and dot RID 678, that is routing indicator, and the scheme 0. Since scheme is 0, you need not have to mention any key, and the MSISN is as it is can be written. So for a profile A where it is being encrypted, in that case, if it is type 0 MCC 234 and dot MNC 15 dot RID 67, and here it is scheme is 1, and scheme is 1, you have to mention the key, and the encrypted string should be mentioned here. And then if you want, you can have this MAC tag value also for authentication or integration purpose. And then we have 5G NR global unique temporary identifier, that is GUTI. 5G GUTI is a temporary identifier, and it is used over the radio access link. And this is allocated to UE by the core element AM network function AMF, and it is 80-bit long, consisting of PLMN plus AMF ID plus TMCI, and its associations is not fixed to a specific subscriber or a mobile. AMF may reassign a new 5G GUTI to UE at certain conditions, at certain situations. Single 5G GUTI can be used for accessing 3GPP as well as non-3GPP technology security context within AMF. So this is the format or scheme of 5G GUTI. It is 80-bit long, 48-bit GUAMI, that is globally unique AMF identifier, GUAMI, and then 32-bit 5G TMC. So this 48-bit again consists of three main components. Of course, these two, MCC and MNC, is a combination to represent the address. And this 24-bit AMFI, it is actually AMF ID. So this contains AMF region ID, that's first component, and then it can mention the AMF set ID if we have a set of AMF. Under that, it can also mention the single AMF ID, that is AMF pointer, which mentions or which points to a particular AMF. And then we have 32-bit 5G TMC, it's a temporary mobile subscriber identity. Suppose this all these applications or communications are happening under a single AMF indicator, the set one single set, then we need not have to mention this address MCC and MNC. We can leave this. So in that case, we can take only these two, AMF set ID and a particular AMF pointer as a particular AMF ID. So by combining these two, that is 32 plus the 16 bits, it becomes only 48 bits, which is called as 5G shortened TMSI, that is shortened form of 5G GUTI. So this globally unique AMF ID structure, that is GUAMI, is 48 bits. This identifies one or more AMFs. When GUAMI identifies only one AMF, then this TIMC identifies the UE uniquely within the AMF. Suppose we have more than one AMF, that is a set of AMF, of course this temporary ID should be unique across that set. I think that you know why it should be unique across the set, because we have more than one AMF. Then it has to ensure that in no other AMF this TIMC is available, or 5G TIMC is existing. Globally unique this AMF ID structure, AMF region ID identifies the region, AMF set ID uniquely identifies the AMF set within the AMF region, and AMF pointer identifies one or more AMFs within that AMF set. And AMF region ID addresses the case that there are more AMFs in the network than the number of AMFs that can be supported by AMF set ID. And AMF pointer by enabling pointers to reuse the same AMF set IDs and AMF pointer in different region. So this I had prepared for my students. This is not required for you people. This is to represent why we have to have the set of AMF, because for a single UE, if it wants to have a different session, there will be more than one AMF and there will be more than one UPF and SMF. Then we have yes TMC structure. So this has three components: AMF set identity and AMF set identity 6 bits set identity, and 5G TIMC. So this, yes, TIMC is the shortened form of GUTI, which enables more efficient radio signaling procedures, example during paging and especially paging and service request. In new generation, RAN uses the 10 least significant bits of 5G TIMC in the determination of the time at which different UEs are paged. AMF ensures that 10 LSB of 5G TIMC are evenly distributed. And this we have already seen, because in 2G, 3G, and 4G network, IMSI or SUPI values are sent in plain text over the radio access link, which was not secure. So that was a security issue up to 4G network. So in order to avoid that security breach, the visiting network or the temporary ID was generated by AMF. When actually AMF provides a new 5G GUTI. Upon receiving registration request message of type initial registration or mobility registration update from UE, the AMF shall send a new 5G GUTI to the UE in registration accept message. That is first time when it gets registered with the network, this 5G GUTI has to be allocated to that. So, or upon receiving a registration request message of type periodic registration update, if there is a periodically that TIMC has to be re-registered, even in that case, if the time is elapsed, even after that time, it gets a request, registration request again, then AMF allocates the 5G GUTI to the UE registration accept message. Then upon receiving a network triggered service request message from UE, that is service request message sent by UE in response to paging message also, the AMF shall use a UE configuration update procedure to and sends a new 5G GUTI to UE. Then we have how actually this GUTI mapping happens between 4G and 5G mobility, because we are working with NAS coverage of the communication system. We have both GNB and ENB and EPC core as well as 5G core. And these mobiles, that is 5G enabled and 4G mobiles, may have to communicate with 5G mobile may have to communicate VPC core, and 4G mobile may have to communicate with this 5G core. In that case, how this mapping happens, that is when a mobile user moves from 5G to 4G, UE actually maps the 5G GUTI onto 4G GUTI and forward to the MME. MME performs a reverse mapping of 4G GUTI to 5G GUTI and finds out AMF from where that MME needs to contact to fetch the UE context, because MME needs to have the information on UE. So for that, it has to perform that mapping 4G GUTI to 5G GUTI and then finds out the AMF. Then it contacts the AMF and gets the information. Suppose UE moves from 4G to 5G. In that case, UE maps 4G GUTI to 5G GUTI and sends AMF. Send to AMF. AMF decode the MME ID to retrieve the user context. So in this case, when UE moves to 4G to 5G, this is how it can get the information. So this is how mapping is happening between 5G and 4G GUTI, because we have NSA communication coverage at the standard. So this is the identifier. This is how the structure or the format helps to do that. That is MCC, MNC 12-bit, 12-bit address, AMF region ID, and AMF. This is how it maps. If AMF set ID is 10 bits, AMF SSID is 6 bits here. So 5G TMC is of course 32-bit. So that is when it is when it gets mapped to 4G mobile, it is 12-bit, 12-bit, no problem here. Here it becomes 16 bits, that is AMF region ID and AMF set ID. This by taking this 2 bits from here and adding this to it, it becomes 8 bits, which represents the MME code. So that is how this mapping is happening. Then we have permanent equipment identifier. Sorry, sir, this is our class bell. So permanent equipment identifier in release 16 of a specification, it may indicate an IMEI or IMEISV, a MAC address or an IEEE extended unique identifier, that is UI64, and an IMEI, IMEISV, a MAC address or an IEEE extended unique identifier for UEs not supporting any 3GPP access technologies as defined in IEEE guidelines for use of extended unique identifier. Originally, it is a unique identifier OUE and the company along with the company ID CID. So this is the format of that as IMEI, International Mobile Station Equipment Identity. It has a type allocation code of 8 digits long, and it has a serial number of 6 digits, and then it has a check digit. It's a separate digit, one single digit. So then we have identifiers of radio access network, that is 5G NR radio network temporary identifier, RNTI. So this RNTI is a radio network temporary identifier, 16-bit identifier it is, and its value depends on the type of RNT. Actually, we have a list of identifiers I'll show you. And the connected UE in the cell is a specific, it has to access a specific radio channel with a group of UEs in case of paging, a group of UEs for which power control is issued by G node B, system information transmitted for all the UEs by 5G GNB. So these are different types of RNTI we have. So depending on the type of channel that you're accessing, you can use appropriate one. Then we have UE radio capability ID because it has a different channel capability, radio channel capability. So to access each one or to work with each one, we need to have a different IDs. So the UE radio capability information contains information on radio access technologies that the UE supports. Example, power class, frequency bands, and so on. The which channel or which frequency band the UE supports should be mentioned here. The UE radio capability ID is used to uniquely identify a set of UE radio capabilities, and UE radio capability ID is assigned either by the serving public land mobile network or by UE manufacturer itself, because that UE is supporting or capable or comfortable with which channel either it can mention or the UE manufacturer can mention it. So with the increase of size of UE radio capabilities driven by additional band supported by RAN, and UE support of significantly more band combination, the size of UE radio capabilities has and will significantly grow from release onwards. Then we have a network identifier. So in network also we have different elements, and in 5G core especially it is software based. Most of the network functions can be instantiated. So we will have more number of network functions. So we have to have IDs, otherwise it will be very difficult to work with all those sessions or group of network functions. So here we have AMF identifier, NR cell global identifier, tracking area identity or registration area, single network slice selection assistance information. These are some of the IDs we have. We'll see one by one. So this is new radio cell global identity, which the new radio cell is given a NCGI, that is new radio cell global identity, and this concentrates it actually concatenates a public network ID, that is PLMN identifier, and 36-bit NCI, that's a cell identity. NCI includes G node B ID, and this is a tracking area identifier. So the tracks or the tracking area will be generally used. The tracks are nothing but a group of cells which will be mainly used in case of paging. So for paging, the user or the UE device may have to notify with the kind of
Hello.
communications it is. Yes.
Hi, good morning. Hi, good morning.
Okay. So whenever the UE,
just a moment, we'll mute everyone there. Yeah, I think you can go ahead.
yeah. So whenever UE is in idle mode, and if it starts getting any kind of communication, that has to be notified. So for that, it has to be located, identified. So for that, we use this group of cells to locate it. So that is called a tracking area. And this tracking area or the tracking area identifier has this format. 5G's tracking area identity has, of course, this mobile country code and network code, and then 5G's tracking area code, which is of 3 bytes. And 5G registration area is a combination of many tracking area. So when do we get, or how to take the combination, how to decide what tracking area should be combined to consider as a registration area is. So suppose, for example, here we have a bus. Suppose if it has some IoT sensor installed in the bus running on a particular route. So suppose if it is moving between this point and the airport every day, it is moving across these 3 tracking areas. So in that case, 5G system learns, 5G systems observes this every day. It is following the same route, and it learns that it is covering these 3 tracking areas. So the registration area for this entity or for this bus will become the combination of these 3 tracking areas, that is tracking area 1, 2, and 3. So paging is done in this registration area for this bus or the IoT, I mean, any device installed within that bus. So it reflects mobility pattern of UE actually, and unique paging area for a specific mobile area it represents. And within its registration area, no need to perform any mobility updates to the 5G core network. So the saving on the signaling resources. Since it learns and does on its own, it saves the signaling resources. And finally, we have this 5G core FQDN, that is fully qualified domain names. So here we have home domain, network domain, and public land mobile network level, and home network function repository function FQDN, network slice selection function FQDN, AMF name and AMF set FQDN, AMF instance FQDN, and SMF set. So home domain, network domain looks like this. We have already seen this kind of domain for 5GC. It is structured like this: 5GC.MNC and .MCC .3GPP. So this is a combination of course, the mobile country code and the network code and 3GPP network. Example, if we have MNC as 12 and country code as 404, it looks like this: 5GC.MNC012 MCC 404 .3GPP network.org. The home network domain is for a standalone non-public network. The structure looks like this: 5GC and .NID. So since it is a non-public private network, we have to mention NID .MNC .MCC .3GPP network. So for example, home network domain for MCC is 404, MNC is 12, and NID 0007 ED9D5. In that case, it will be 5GC .NID 007, it's ID, and .MNC network code .MCC country code .3GPP network.org. So this is how it will be structured. And then we have PLMN level and home network, network function repository function. As we know, this network repository function is the one where all new network functions will be registered with this network. It will be available, the complete information about all the network functions which provides various services will be with NRF. So any other network function which, if it wants to have any kind of service, it has to contact NRF and gets the information. So when NF is instantiated, it registers with NF, a repository function, then discover other NF instances querying the NRF. So the IP address, so for that, if any network function in the core wants to access or wants to talk to NRF, it should know the address of that, right? IP address. So the IP address or FQDN of NRF is provisioned into the NF. So NF can also self-construct the NRF FQDN. So within this public network, it can be structured like this: NRF dot 5GC dot MNC dot MCC, that is country code and the network code dot 3GPP network. And for this example, for MCC 404 and MNC 12, the API root of NRF services shall be this link. In that case, nrf5gc.mnc012, MCC404 and 3GPP network.org. If it is private network, of course, we have to mention NID, the domain network ID. So it will be like nrf5gc.nid as a code mnc012.mcc404 and .3gpp network.org. And then network slice selection function FQDN. So for this, as you all know, when we have, I mean, if any user can have maximum 8 slices, right? Even though there can be n number of slices, every user can access only 8 slices. So in that case, this NSSF, NRF, and AMF are the common functions, network functions, which will be dealing with or maintaining all these slices. So when we have more than one slices, as usual, when we have more than one entity which is trying to access the same some kind of service, it has to have some ID for efficient maintenance and management. So that is why we need to have a single network slice selection assistance. I mean the ID, that is identification of network slice, is done via single network slice selection assistant information, that is NSS AI. Currently 3GPP allows up to 8 NSS AIs in the NSS AI sent in signaling message between the UE and the network. This means a single UE may be served by at most 8 network slices at a time. The NSS AI is signaled by the UE to the network, assists the network in selecting a particular network slice instance. Then AMF name FQDN. So here the AMF name FQDN uniquely identifies the AMF. In public network, it will be mentioned like this AMF ID. And in that set AMF, what is the AMF ID with which you are talking to or having a service? .amf.5gc.mnc.mcc, then .3gpp network. So if it is private network, of course, you have to mention this NID. All other things are same. And fully qualified domain names structure is like this. It consists of 3 components: AMF region ID, AMF set ID, then AMF pointer to point to the particular AMF. AMF set, of course, you have to mention the set ID, set AMF set ID dot region, AMF region ID dot AMF set dot 5GC dot network code, country code, then 3GPP network.org. So for example, set 001 dot region 48 dot AMF set dot 5GC dot MNC 012 is a network code, and the country code 345, and 3GPP network since it is a public network. AMF instance, and for SMF set, you can mention, you can take this format. It's almost same. That's about different types of identifiers we have in 5G for flexible maintenance of the entire communication. And thank you. And I have taken the resources, PPTs from these links. Mainly, I have taken PPTs from Ashok Kumar sir's class. Thank you so much, sir.
Thank you. Maybe there may be any question from any participant. If there's no question, Madhukar, if you can offer formal vote of thanks to ma'am. Madhukar?
Yes, sir.
Ma'am, if you can unshare your screen in the meantime.
Yes, sir. Yes, sir. Yes, sir.
So
Thank
it was a wonderful presentation by Professor Dakshayini Madam on 5G numbering, addressing, and identities. On behalf of the team and participants, I feel honored to extend sincere thanks and gratitude to Professor Dr. M. Dakshayini Ma'am for her effort and contribution to this
Thank you,
faculty
sir.
development program. Ma'am, let me know everyone that you got very little time for this session, but the session was very excellent, informative, insightful, and displayed your deep understanding and grasp on the subject. Once again, I thank you for your contribution for making the overall content of this FDP on 5G rich and diverse. A special thanks to all the participants also for their time and involvement, which made this session fruitful, successful, and with live and vibrant atmosphere. Thanks all of you. All regards. Jai Hind. Thank you.
Thank you, sir. Thank you so much. Sir.
Thank you, ma'am. Thank you so much. I think
Thank
our
you for the
next speaker.
opportunity, sir.
Thank you. And our next speaker is already there with us. Madhukar, in the meantime, if you can stop